Well, that's 6:30 and already 42 people are here. So welcome everyone. Oh, where'd my chat go? This is going to take some getting used to. So I don't have an hour and a half of material planned. I just sort of guessed at the time that we should take. I didn't know if it should be an hour or an hour and a half, so I guessed an hour and a half. So we might not go the entire time, we'll see. One thing I thought we could do is go over the old exam, if that seems reasonable to people. So here's an example of a mass spec problem. Oh, and I have to get the spectrum too. Geez. I don't know how I'm going to be able to show everything on my screen all at once. Truth is, I can't. So there's the mass spectrum of the compound in question for heptanone. And the only peaks we can't put down as answers are the ethyl cation and the molecular ion. Molecular ions over here at 114. It even says massive molecular ion 114. So let's see if we can pick some low-hanging fruit here. Here at 15 is going to be CH3 plus. So you're right, CH3 plus M over Z equals 15. Whoops.
Dr. Wass, are we currently just listing out as many as possible, or are we?
That's what I think we'll do.
Okay, thank you.
We only need 3. We already have CH3, CH2 plus in the example given. At 43 should be, can you explain how you know it's 15, like where you're getting it from? Yes, I sure can. 15 comes from 12 for carbon plus 3 times 1 for hydrogens. So you'll just get those from the periodic table. So 12 plus 3 is 15. So that's the format you use to write down the answer. And we already were given 29 for ethyl. Let me show you how you get the ethyl one. Where you get the 29 from is there's 2 carbons, 2 times 12 is 24, plus there's 5 hydrogens. 24 plus 5 equals 29. Does that answer the question about how you get them?
Yeah.
Please ensure that your microphones are muted. Oh, yes. I should be able to do mute all.
Which question are you talking about in this? Is this the one that has the mass spectrum and that?
Oh, yeah, I'm sorry, I just muted you. Yes.
No, it's okay.
Yeah, I figured I would just, I figured I would start by going through the practice exam.
Ooh. Oh, I mean, like which one? Like the one with the spectral data, or the form B, or the
Right.
form? Oh, you're
I
in form
figured,
B.
yeah, the same one
Okay.
that you have on Canvas.
Okay. There's like another one too. There's like the one. This one doesn't have any mass spectra. It's just like the more reactions, and it has like oh, I guess it does. It's the one that has like the actual, like it looks like an exam.
Right, but this is the only one that has, this is the only exam 1 that I put up. So
Could you please
Oh.
tell us what the compound is again, Dr. Wass?
the compound is 4-heptanone. Let me try drawing it for you. That's 4-heptanone. And we can do this one more time. And if you add up 3 carbons and 8 hydrogens, you get 3. Sorry. Oh, how about CH3, CH2, CH2? That'd be a little better. 7 hydrogens, then you should get 43. So that's 2 answers right there. We can't use this one because it was given in the example. And here's another peek at 99. 99 is 15 less than 114. So 99 would be the whole molecule minus a methyl group. In other words, so again, what I did is I took the 15 for the methyl group and subtracted it from the molecular ion. And I saw a peak there at 99. So this would be CH2 plus over here. It's the molecule minus a methyl group. Okay, I don't know what to do about raised hands. I guess, can you
Oh.
unmute yourself?
Yeah, I could just. I was just waiting. Could you mind making like the ChemDraw full screen? It's just kind of hard to see, or like split screen it, because it's kind of hard to see on like the Zoom.
I don't think it'll, wait, why did you take away the line and add a methyl group? I don't think it'll make anything bigger though.
Maybe like the Windows sign and like right click, because that split screens it for me at least, and it's easier.
I can go like this.
Oh, that's better. Yeah, I just can't really see it on my end.
Okay. So the reason oh, wait a minute. Didn't expect to run out of real estate so quickly. So the reason I took away a methyl group is because a methyl group weighs 15 and 114, which is the molecular ion, that's how much the molecule weighs, minus 15 equals 99. And I saw a peak at 99, so that's what I think this one is. So that's 3 answers right there. Let me look at the answer key and get a couple more. So that's the one at 71. I thought so. I'm drowning in windows here. So the one at 71 comes from an alpha cleavage where we break this bond. And the plus charge then goes on this side. With how relatively simple the math is for these problems, I'm assuming that calculators will not be needed for this exam. Is this correct? I don't think you'll really need them, but you may use a calculator. Just because I would feel terrible if someone got something wrong just because they didn't have a calculator. So you may use a calculator on this exam. This is mass to charge ratio is 71. How do you know where the plus charge goes? Does it always go on the alpha carbon? Yes, always. It always goes on the alpha carbon because it's an alpha cleavage. So that's 1, 2, 3, 4, and we only needed 3. There's probably others. You could probably do a whatchamacallit, a McLafferty rearrangement also. But I don't want to spend all the time on just this one problem. What is the alpha carbon? Can we do a lot of chapter? Yeah, I want to spend more time on 15 and 16. So actually, I don't think there are all that many reactions in chapter 15. It's mostly whether something's aromatic or not. Yeah, 16 is where most of the reactions are. There's a few in 14, but they're mostly in 16. I can't say directly whether this or that particular thing is going to be on the exam. Naming is certainly fair game. Is it preferred that we draw out the skeletal structure? Is the written out formula acceptable for these problems? You're talking about mass spec again. You'll need to draw the structure, not just the formula. In other words, not C7H14 plus or something like that. We'll need a structure. So I think that about takes care of the mass spec problem. Should I spend any time on IR or carbon 13? Or do you just want me to go straight to chapter 16?
I think we should spend a little bit of time on IR. Or
Okay. Well, yeah, these are IR spectra over here, so we can certainly touch on it. The first IR spectrum looks to me like there are peaks both just above and just below 3000 wave numbers. Remember, that means we have hydrogens attached to both sp2 and sp3 hybridized carbons. There's also a very prominent peak here just above 1700 wave numbers, which is the area that we expect to see carbonyl stretching frequencies. Remember, carbonyl is C double bond O. So we're looking for something that has either an alkene or an aromatic ring and a carbonyl group. Find the actual exam. So the only thing that fits that, D has a carbonyl group, but it doesn't have any sp2 hybridized carbons other than the carbonyl. So I think the correct answer has to be B for that one. That's spectrum S, which we just looked at.
Dr. Wasp, where was the alkene in there?
If you draw an imaginary line at 3000, there's some peaks just above 3000 wave numbers and some peaks just below 3000 wave numbers.
I was talking about the diagram, the actual picture of the molecule.
Well, it means that there's either an alkene or an aromatic ring, and B has an aromatic ring.
So having some number, if there are some wave numbers that are above 3000, that could be an aromatic.
Aromatic or alkene, yes.
I thought an aromatic was if there was 1900, like it was like between 1900 and 2000.
Well, B is the only one that has both an aromatic ring and a carbonyl. This is so double bond O, OCH2CH3.
Okay, so an aromatic could be like an alkene. Both of them could be above 3000 wave numbers.
That's correct.
Okay.
So how do you differentiate alkenes from aromatic rings? Well, you can find these little overtone bands here. That's a sure sign that you have an aromatic ring. But in any case, we didn't need to, because B is the only compound that has both an aromatic ring and a carbonyl. So it has to be B.
For spectrum U, would you say that's a carboxylic acid, or is it not big enough?
Let's see. Well, can we take care of T real quickly beforehand? T is definitely an alcohol. You can tell from the OH stretch over here, and I think there was only one alcohol. Yeah, A. So T has to be A. Let's look at spectrum U. No, that doesn't look like a carboxylic acid to me. Looks to me like not much of anything going on here. We just have some peaks below 3000 wave numbers, which means that it's saturated. I don't see a carbonyl. I don't see an alcohol. If it were a carboxylic acid, this would be much bigger and possibly obliterating the entire high frequency end of the spectrum. So this looks to me like it's got nothing, like it's just an alkane. And the only compound like that is E. If you compare that to spectrum V, now we have some peaks above 3000 wave numbers. I don't see any overtone bands, so I don't think this is aromatic. But I don't see a carbonyl, I don't see an OH group, I don't see anything like that. So it looks to me like just an alkene. And the only alkene we've got is F. I went through that rather quickly, but I sensed that people wanted to get onto the reactions.
Yes. I missed the first part. What did you say that was the first, what is it? Well, what was the question? Oh, what is S? I missed that part. Is that one B?
Yes, that's B.
Okay, cool, thank you.
have a question. Which peaks are associated with the aromatic ring again?
The CH stretches will be just above 3,000 wave numbers. And then you'll also see the overtone bands, which are right around 1900 or 2000. They're pretty small, but they're generally small and round.
Thank you.
The Carbonell peak is the one at 1700, right?
Yes, indeed.
Thank you.
All right. Might as well look at the carbon NMR. This first one, I see 5 peaks, which means there's 5 types of carbon. This one here above 200 parts per million has to be the C double bond O. Can I just start saying carbonyl for C double bond O? I think I've introduced that term enough. So that's going to be a carbonyl, probably a ketone. And then there's 4 other carbons that are in the alkyl group range, or pretty close to it. This one at 45 has got to be next to something, maybe next to the carbonyl. So we're looking for something with 5 types of carbon that has a carbonyl in it. And let's see. These 2 have carbonyls, but way over 5 types of carbon. These 2 have carbonyls. So the question is, which of these has 5 types of carbon? And I think it's H, because this methyl group and that methyl group are different. These 2 CH2s are different. One of them is next to the carbonyl and one of them's not. So all 5 of those carbons are different. So I think spectrum W is H. Where do you find the spectra booklets? Should be on Canvas. You should have a copy of the exam, the spectra booklet, and the answer key available on Canvas. Sorry. The next one looks like it is a carbonyl of some type also. It may be a carboxylic acid or an ester. There's then 5 peaks in this area, because it says between 120 and 135. And then there's a 6th peak over here. So these are in the aromatic range. 120 to 140 is very typical for aromatic carbons. So we're looking for an aromatic compound where all 6 carbon atoms are different. And then we also have 1 peak in the alkyl range. So we're looking for a carbonyl, an alkyl peak, and 6 different aromatic carbons. And I think there's only one compound like that, which is G. All 6 of these aromatic carbons are different. In J, there's a plane of symmetry running down the center of the molecule. So you'll only have 1, 2, 3, 4 types of aromatic carbons. So I think G is the best answer for spectrum X.
Why? Because that's a carboxylic acid. Or how is there carbonyl anywhere?
Carboxylic acid is C double bond O, then OH. So it has a carbon.
Okay.
So spectrum Y, where's spectrum Y? Looks like there's only 3 types of carbon. And yes, we can tell something about the different carbon types. Maybe these are 2 carbons each. I don't know, but there's only 3 types of carbon. And it looks like 2 of them are in the alkyl range, and 1 of them is bonded to something electronegative. And I think the only one that fits the bill is L. Because K is more than 3 types of carbon. K has 4. L has 3. These 2 are the same. These 2 are the same. And that's CH2. What was spectrum W? Spectrum W was H.
Can we go over the one right below W again, please? Really quickly, sorry.
You mean X?
Yes, sir.
So this one has 6 peaks in the aromatic range. There are 5 between 130 and 120 and 135, and then the 6th peak. So there's 6 different aromatic carbons. There's also a carbonyl and 1 alkyl type carbon.
Okay. So there's only an aromatic, and is there a carbonyl? There's
Yes, this is a carbonyl peak over here. That's where ester and carboxylic acid carbonyls show up.
okay. Thank you.
And so the only one that fits that description is G. In J, all 6 carbons are not different. There's this one. There's these 2 that are the same, that are ortho to the carboxylic acid group. There's these 2 that are the same, that are meta to the carboxylic acid group, and there's this one that's attached to the methyl. So that's only 4 aromatic carbons. We have 6, so it has to be G and not J.
Thank you.
And then last but not least, spectrum Z, which has only 3 types of carbons. 2 of them are in the alkyl range, and 1 of them is a carbonyl, probably a ketone. So we need something that fits that description. There's only 3 types of carbon. And the only compound that fits the description is I, because there's the carbonyl, that's 1 type. There's these CH2s, which are the same, that's another type. And then there's the 2 CH3s, which are another type. So much for carbon NMR. What about K? K is not one of them. K would have 1, 2, 3, 4 types of carbon. All 3 of these methyl groups are the same. And there'd be, isn't that an O double bond C? No, these are single bonds to oxygen. Spectrum Y was L. Let's see. Yes, spectrum Y is L.
Dr. Wass, how do you know if the carbon is double bonded to O or single bonded to O? Based on
Well, if this were a double bond, carbon would have 5 bonds.
okay. And what about the carbonyl group in G? How do you know that that was a double bond?
I'm trying to get better about writing out carboxylic acid groups, C double bond O, OH.
Okay. Thank you.
So I sense people want me to get onto the reactions. So please practice these types of questions.
Oh, for this one, I did the one with the like ATO. The most stable was, sorry to spoil it, but the most stable was when
The
there was
answer
a
key is available anyway, so you're
Well,
not
I know,
saying anything.
I know, but I was doing it like literally earlier, and I don't. O had a positive charge as one of the resonance forms, and that was the strongest that was like the most stable, and I don't understand why, because I feel like O doesn't usually like to be positively charged. So I don't understand why that would be the
Well,
most.
there's H3O plus. Can you actually do the highest value and lowest value right above it? Oh, you want to do this one. Well, the highest value of lambda max is going to be the one that has the most conjugated double bonds, and that's going to be A. That has 4 conjugated double bonds. And the lowest one is going to be the one with just the 1 double bond, with no conjugation. So I think it should go B, C, D, A.
Is it because the more double bonds there are, the more it can absorb?
The more
Or-
conjugated double bonds are,
Okay.
the
Yes.
higher the wavelength of absorption, yes.
Thank you.
So we were talking about this type of problem.
Yeah, the most strong resonance had a plus charge on the oxygen, and that's why I'm confused about why that was the best resonance form. Because like I feel like the oxygen wouldn't want to be plus, so why would that be the why would that be the most stable?
Well, again, oxygen can have a plus charge, like an H3O plus. So there's nothing strange about that.
Okay. Is that so it's better than is it because it's tri-substituted when it's like that? Would that be the only reason? Or no?
Well,
I mean, like why is it stronger when it's like when the positive charge is just on like a secondary position?
I think it's more favorable to put a plus charge on a heteroatom than on carbon.
Okay, that makes sense. Thank you.
That's what I would say anyway. So practice drawing intermediates with resonance forms. Outside of the benzene ring, that probably also helps. Good, and of course the one that's aromatic is pyridine. The others are all either non-aromatic like this one. What would the best resonance form be? Well, this one over here. And I mean, maybe you could argue that a little bit. I can see how someone might think it should best be on the tertiary.
Yeah, that's what I thought, because it seems like it'd be the most substitute or like the most substituted area, but that's why
I
I'm
think it's
confused.
best having it off the ring. 'Cause
Okay.
it's like a carbonyl here now.
All right.
That's a minor point though. So please, can you explain why the lone pairs on the nitrogen are not included when we're counting electrons? Because they're in the sp2 hybrid orbital. And I can try to make a diagram. I practiced doing this yesterday on purpose because I thought this might come in handy. Why are there 3 double bonds in the second one? Or are we looking at the answer?
I think she means like one of the resonance forms has 3 double bonds. Yeah, like the one that's circle, it has 3 double bonds.
Right, because you get another one by having the oxygen share the plus charge. It comes by the oxygen donating an electron pair in and making this a double bond.
Wait, Dr. Was, I'm sorry, I'm just still a little, why is the tertiary not more stable than the oxygen, the oxycation? So,
I don't know if I have a first principles answer for that. I probably should. I think it's because the carbon-oxygen double bond is strong.
Okay, thank you.
Gets the plus charge off the ring. Does conjugation matter in this case? Well, that's also true. You also get all of them conjugated that way. Good catch. That probably also helps explain it. When the extra double bond is introduced, it further stabilizes the system too. Yes, I would say so, since everything's conjugated now. See, here they're not conjugated, even though it's tertiary. Good. So would you like me to make the diagram for pyridine, or are you fine with me saying, whoops. I practiced this special the other day.
What are all the four rules again, Dr. Voss? I just
The compound must be cyclic, must be planar, must have all of the ring atoms be sp2 hybridized, and then the 4n+2 rule. There has to be, yeah, cyclic conjugated.
thank you. Thank
And the number of pi electrons needs to be 2, 6, 10, 14, etc. Now let me see if I have a hybrid orbital. That looks kind of like a hybrid orbital. That wasn't what I wanted. So that's an sp2 hybrid orbital on nitrogen. So first, all 6 of the p orbitals get 1 electron in them because they're involved in pi bonds. So that's pretty much by definition. And then the only place left to put the lone pair on nitrogen is in that sp2 hybrid orbital. So it's not included in the pi system. The pyridinium ion is also aromatic. Which has a plus charge on nitrogen. And in that case, the NH bond goes into that hybrid orbital. So the cation is aromatic also. Good. Well, again, I'm feeling some pressure to get onto the reactions. So we're finally done with the spectra. So here's some good examples of reactions. So for these types of questions, all you need to do is draw the product. draw the major organic product. So I don't want to start with one that's multiply substituted, though. I want to just remind you of can you label what kind of reaction each is? No, not directly. I have to open it in ChemDraw first. So this first one is electrophilic aromatic substitution. Or if you want to get more specific, electrophilic aromatic nitration. This one here, you remember what NBS is? N-bromosuccinimide? Bromination of benzylic carbons. That's what NBS does. Actually, it might make more sense if I did this on the answer key. I just don't want to put those things on. Because that way we could see the answers also. Where's the answer key?
Dr. Wass, where's the part of the notes where it has the list of what's ortho, para, meta, and all that? Which part?
I don't know that I put that in the notes, but I have to open up another window. But I made reference to it. Substituent effects. There you are. Pages 494 and 495, table 16.1 and figure 16.11. That's where you find orthometapara.
Thank you.
So let me go back and do what I was doing before. That's electrophilic aromatic nitration. This is bromination of benzylic carbons by N-bromosuccinimide. This is oxidation of aromatic alkyl groups by potassium permanganate. And over here, this is a Friedel-Crafts alkylation. This is a Diels-Alder reaction. And this at the bottom is from organic 1. This is epoxidation of alkene. I was a meanie that year and put a reaction from the first semester. It's fair game. It's organic 1 material. Are there resources or chapters you could recommend for OChem 1 reactions? Yes, 8 and 11. 8 and 11 are the major ones. I guess in 17 also. Those are the ones we usually make the most references to. Also, I recommend you look at my Organic 1 class notes for Chapter 8, because I have in there a step-by-step method for learning reactions.
Did we learn the one with potassium permanganate, Dr.
Yes,
Watt?
we did. I went over that in class. Repeat that, please. 8-11-17. Professor, where could I find your YouTube channel? My YouTube channel is R86 Chemistry. Like that. And again, I'm not going to be able to get this up tonight. It'll probably be sometime. I'm going to try to get it done tomorrow afternoon. I hope I remember how to do this. So, wow, half the time is gone already. So does this answer the question of what types of reactions they are?
Yeah, thank you so much.
Okay.
Dr. Walsh, could you please explain reaction number 1 and reaction number 3?
Yes, this one is if you treat an aromatic ring with nitric acid and sulfuric acid, it replaces one of the hydrogens with the nitro group. And so we need to figure out where the nitro group's going to go. We have the methoxy group, which is ortho-para-directing. And we have the chlorine, which is also ortho-para-directing, but is disagreeing with the methoxy. So remember what we said. The group that wins is the one that's more activating. And the methoxy group is more activating than the chlorine. You know that from its position in the table.
Isn't it also because OCH3 is bulkier than Cl, therefore reducing steric strain?
No, but that does have an effect.
Okay.
It means that we're not going to want to put the new group here or here. We want to put it over here where it has the most room, because methoxy is bigger than chlorine, as you correctly stated. So I think that's where the nitro group's going to go. And this reaction basically any alkyl group on a benzene ring, if you treat it with potassium permanganate, it's going to turn the carbon that's attached directly to the benzene ring into a carboxylic acid group. Again, this is C double bond O, OH. It's a carboxylic acid functional group. And any other carbons in the alkyl group get oxidized all the way up to carbon dioxide. So let me put something here on I just want to return that to the state it was originally in. What was I talking about? This reaction. So I already have a benzene up there. Basically, what you need to know is any compound of this type that has at least one benzylic hydrogen. When you treat it with aqueous potassium permanganate, you get benzoic acid. And here I won't write CO2H. I'll actually write the group out. Makes it easier to see. So that's the reaction. And this is just like that. Here's a benzylic carbon that has at least one hydrogen on it. That's going to get converted to the carboxylic acid. So there's your carboxylic acid functional group. The chlorine doesn't do anything. The next one is a Friedel-Crafts alkylation reaction. This again is actually C double bond O, OCH3. This is an ester functional group. Like I said, I've tried to get better about actually writing these groups out and not abbreviating them, since I've noticed students are confused when I abbreviate them. So this is a carbonyl directly attached to the benzene ring. That's a meta-directing group. And that puts the tert-butyl group in the meta position. Should I go over the Diels-Alder reaction?
Yes.
So there's our diene. Again, I think the dienophile looks confusing because I didn't write out the ester groups. So that's what the dienophile looks like. And in class, I drew dotted lines here. You can if you want to, you don't have to. And so what you get is a cyclohexadiene. And that's what you get. As it says on the answer key, no wedge or dot bonds. The molecule's flat. At least this part of the molecule is flat, and this part of the molecule is flat also with the methyl group. What if it wasn't flat? Well, then you would have to show the stereochemistry. Let's do another Diels-Alder reaction. Is it okay if I abbreviate C triple bond N as CN? I'm just trying to save a little time here. Same mechanism as before. And now, since the cyano group started out cis in the dienophile, you will agree that these two CNs are cis to each other. Then they will also be cis in the product. And we need to show stereochemistry, either two wedge bonds or two dot bonds, but they need to be cis. Do we need to show the electron flow for the test? It depends how the question's phrased. If the question is a mechanism question, then yes, you need to show the electron flow. Otherwise, you have to do everything it says. You don't have to do anything it doesn't say. So that would be an example of one with stereochemistry.
Dr. Wass, how do you know if you need to show like stereochem? How do I know if it's not planar? Like, how do I know that the cyanide needed stereochemistry?
Well,
Like,
because these carbons are sp3 hybridized. sp3 hybridized carbons are not planar. And since they had stereochemistry in the starting material, that stereochemistry is maintained in the product. So the
Oh,
way you know it's not planar is if they're sp3 hybridized carbons.
it's only planar if it's sp2.
Right.
Okay, all right, thank you.
I feel like I want to do some more electrophilic aromatic substitution reactions, though. Should we go over this question here? I forgot how to tell if the bonds are cis or trans. Could you please remind me? Yes, these two cyano groups are on the same side of the double bond. They're both to the right of the double bond. That means they're cis. So that's how you tell. Good. Let's do more electrophilic aromatic substitution reactions. So let's do this one. Tert-butyl bromide plus aluminum bromide. Let's do the mechanism and everything. There's tert-butyl bromide. We also need aluminum bromide. And to get the product, remember how you do this. You look where the halogen is. You pull the halogen off and you replace it with a plus charge. And so the first step of the reaction, if you're drawing the mechanism, is you show the carbocation. Can you see how I pulled off the bromine and replaced it with a plus charge? That's the carbocation you start with.
If a question was asking to show like the mechanism of the Friedel-Crafts alkylation, would we have to show the step with the bromine being pulled off, or could we just?
That's in the answer is no, that's in the class notes. You start with the carbocation. The class notes say exactly what you have to show in every single case.
Okay, thank you very much.
So we have our tert-butyl group here, not very well drawn. And this hydrogen was there to begin with. So that's the first intermediate. You should be able to draw the other two resonance forms as well.
Dr. Wass, do we have to show the aluminum bromide taking off the bromine from the alkyl halide? Alkyl halide?
No, that's in the class notes.
Okay, thank you.
But you will show the aluminum bromide, the tetrabromo aluminate ion. You'll show, recall we have the tetrahaloaluminate or tetrahaloferrate ion pulling off that proton, expelling a halide ion to pull off the proton. We break the carbon-hydrogen bond. The electrons go back into the aromatic ring, and you get your tert-butyl benzene. So those are the two steps you'll show, if that mechanism's on the exam.
Dr. Wass, I thought the bromine gets the electron, then you get a bromide ion, and then the bromide ion attacks the hydrogen.
I don't think so. I think it actually comes from the tetrahaloaluminate ion.
So it just comes that bond between bromine and AlBr3 just attacks hydrogen.
Right.
Okay, thank you.
I want to do one with a group already on it too. Just I keep running out of room. Let's just put a methyl group on. So let's make two questions out of this. First of all, what's the product? And then after we figure out what the product is, what's the mechanism? So in order to know what the product is, you need to know that alkyl groups are ortho-para-directing. That's in that table referenced in the class notes. So we also said in class that it's reasonable to assume that the para product will be the major product. So I think the major product will have the chlorine para to the methyl group. Like that. As for the mechanism, recall that the first thing you show is the halogen attacking the aluminum or iron. Like that. And you get, whoops, wrong one. You get this intermediate. Then you need to show this aromatic ring attacking from the para position. So we want to show it getting attached over here. So we break this bond. Oh, I want a curved arrow. So we break this bond. Remember that it attacks the end chlorine or bromine. So something like that. No, let's put the H over here. So the plus charge is over here. And then you get this intermediate. The aluminum or iron halogen bond picks up the proton. Breaks the carbon-hydrogen bond. The electrons move in between those two carbons and get rid of the plus charge. and you get the product. Can you explain why for a second mechanism on page 6, we have to form the benzyne intermediate instead of only creating the carbocation intermediate? The reason is that there isn't an electron withdrawing group on the ring. NH2 isn't electron withdrawing. So you need to have nitro or something with a carbonyl or something like that in order to avoid going through benzyne. Is that kind of what you meant? What distinguishes electron withdrawing from not? Well, the groups that are electron withdrawing have a lot of plus charge on them. For example, nitro group. Remember the structure of the nitro group.
NH2 has a negative charge. Is that true, Dr. Wallace?
NH2 minus does.
Okay.
Just the group NH2 doesn't. Remember, the nitro group looks like this. It is a full plus charge on it. So that's why nitro is electron withdrawing. There's a plus charge on nitrogen. The reason carbonyl groups are electron withdrawing I don't know why it's doing it that way, but we'll go with it. Is because there's another resonance form that puts plus charge on carbon. And so if you attach a carbonyl group to the benzene ring, it's going to be directly attached to this carbon that has a partial plus charge. So those are going to be your main electron withdrawing groups. Let's see. So yeah, that one doesn't go through that one you have to go through benzyne. If that were NO2, then you would go through the other type. Let's see. We've already basically done one like this. Oh, except this one has a carbocation rearrangement. So you first have to show the carbocation rearranging, but we did the same thing to start with. We pulled the bromine off and put a plus charge there. Then we show the carbocation rearranging. It goes from a primary carbocation to tertiary. Then the aromatic ring attacks. You get this intermediate. And just like before, the tetrabromoaluminate ion donates a bromide ion to pull off the proton. We push the electrons in the carbon-hydrogen bond back into the aromatic ring to get rid of the plus charge, and you get your product. This is almost exactly like the one we just did earlier. except we had a methyl group instead of an ethyl group. So the mechanism's the same. One that we haven't done, would you guys like to see a nucleophilic aromatic substitution?
Dr. Wasp, could we first would you mind if we could look at the other questions that are left over on the test? I think we might be getting closer to the end of the practice exam.
Over here, that is the end.
Oh, okay. Thank you, sir.
Yeah, this one is the last question. Uh, So let's go ahead and put a nitro group on. Now we know it's going to go by the normal non-benzyne mechanism. And if we put a leaving group up here, and we treated this, let's say, with sodium ethoxide and ethanol, you would expect to get the ethoxy substituted compound. So the way you know it's a nucleophilic aromatic substitution is by the nature of the reagent that you're treating it with. NaOET is a nucleophile, ETO-. So that's how you know. You need to look at the reagent that you're treating the aromatic ring with. If this were an electrophilic mixture, like bromine and AlBr3, then we would be doing an electrophilic aromatic substitution. But since it's a nucleophile, so I'd say that's one thing you have to know. You have to recognize electrophiles and you have to recognize nucleophiles. And I remember there were some questions like that on active, where you had to recognize that very thing. So the first thing that's going to happen is your ethoxide ion is going to get involved. And remember, we went over this in class. NaOET means ETO-, right? The sodium ion's not involved. We don't draw it, we don't pay any attention to it, we don't acknowledge it. We just use the ethoxide ion. So the ethoxide ion, I don't want that one. I want this one. Attacks in the same place as where the halide is. Then we push the electrons onto the next carbon, or you could push it onto this carbon or onto this carbon. Those would be equally acceptable. They're just the other resonance forms. And this carbon, nope. This carbon's going to have a minus charge and a lone pair. Then recall in the next step, the lone pair with the minus charge comes back in between those two carbons. We lose the leaving group. And we get the product. So 2 steps. As long as you've got at least 1 electron withdrawing group.
Thank you, Dr. Wass. Have a good day.
Thanks. See you later. Well, there's still 9 minutes. Should we do an electrophilic addition to a diene?
Yes.
There's a diene, conjugated diene. So recall that at low temperature, we get the 1,2 product. Which looks like this. If this were HBr, of course, you'd have a bromine over here instead of a chlorine. If it were Br2, you'd have bromines on both carbons. And the mechanism of that reaction involves the double bond picking up H+ from the electrophile. That puts a plus charge on this carbon. And of course, don't forget that's a resonance stabilized species. I'm just reminding you of it. Normally, we don't draw both resonance forms unless the problem specifically says to. But I just want to remind you that it is a resonance stabilized species. If the chloride ion attacks over here, then you'll get the 1,2 product. If you're at high temperature, then instead the chloride ion will attack in the other position. And you'll get the 1,4 product. Can you please touch on understanding what an ideal solvent would be for nucleophilic aromatic substitution, as in page 5, third problem? Let's take a look. Oh, you want it to match. Do you see how this is? First of all, IPR stands for isopropyl. So you have IPRONA, and you just change the Na to an H, IPROH. So you just make the solvent match whatever the nucleophile is. At least if it's an oxygen-based nucleophile. I guess you'd also do it for NaNH2. You add an H and you make it NH3. That's your solvent. Oh, here's 1,2 and 1,4 products at low temperature and high temperature. Well, I don't know what else I can do in 3 minutes. For reduction, can we use PT as well as RH? I think so. I might use RH. If it were me in real life, I would use rhodium just to play it safe. Also notice that the hydrogen adds on the same side of the molecule, so any groups that are on there wind up cis to each other. What's happening in the third one? That's a nucleophilic aromatic substitution. The isopropoxide group is attacking this carbon here. You get a carbanion. Then the carbanion folds back in and kicks out fluoride, and you get this. This is a nucleophilic aromatic substitution reaction. Hexafluorobenzene is a good substrate for nucleophilic aromatic substitution. I think we gave an example of that in class. Yeah, you can see what IPR means over here. This is the IPR, isopropyl. Well, again, I've got a minute. I don't think there's any other questions on this page. This is a Diels-Alder reaction up here using benzene as the dienophile. We'll end with that. I'll make sure that we know what all reactions these are. This is reduction of an aromatic ring with hydrogen. This is a nucleophilic aromatic substitution. And over here, we've got two different electrophilic additions to a diene. At low temperature to give you the 1,2 product, which is the kinetic product, and at high temperature to give you the 1,4 product, which is the thermodynamic product. So that time went fast, but I appreciate you all coming. And I hope that was at least a little bit helpful. And I'll see you in class either tomorrow or on Wednesday. At least that's the plan. Stop recording.